Okay, let's look at the solutions for the kinematics and mechanics practice questions. Let's do it. Okay, so the first question is about a particle that moves in a straight line so that its position, x meters, relative to some origin O at a time t seconds is given by this position function. Okay, so from that, let's find the initial position. So the initial position is when time is at a starting point, when t is equal to 0. Okay, so from t is equal to 0, we're going to do that substitution. There it is, and we get just 5 meters, and that's this constant here. Now, what about the initial velocity? Well, from the position function, we got to get the velocity function. So that is the derivative, the first derivative of position with respect to time. And there we go. It gives us a 3t squared minus 8. And now the initial velocity is when we substitute t is equal to 0. Very good. Let's substitute that in, and we're going to get a minus 8 meters per second. Okay, so it's being negative velocity, it means we're heading in the opposite direction. Alright, so part C, what is its displacement after 4 seconds? So what do we remember about displacement? Well, displacement is that change in position. Okay, so that's important. So it's the final position, subtract the initial position, and that gives you a change in position. So the final position is when t is equal to 4. So we've got to substitute t is equal to 4 into the position function, subtract our initial position. That's what we worked out from part A. Alright, we call that the change in position, and that's our displacement. So off we go, perform the substitution, there it is, and that gives you a displacement of 32 meters. Alright, so how'd you go with that? Next questions. So part D, it's time and position when the particle is stationary. Okay, so we got 2 parts here. We've got to get the time when the particle is stationary and then the position when the particle is stationary. So how do we interpret when the particle is stationary? Well, stationary means not moving, so that means its speed or velocity is 0. Okay, velocity 0 is the important piece of information there for when a particle is stationary. So we got the velocity function, there it is, and now we're going to solve this velocity function when it is equal to 0, and we solve for t. So square root both sides, and there it is, gives you that 2 times root 6 on 3 seconds. Now that's our solution, and we take the positive square root value because time is greater than 0, time is positive. Alright, now from that time, let's work out the position at this time. We do that via substitution. So substitute that time, there it is, into the position function. So there you go, it gives us approximately a negative 3.7 meters in its position. Okay, next part, let's work out the average speed in the first 4 seconds. So an average speed is thinking about the average rate of change of position over time, or with respect to time. So you work out the change in position and you divide it by the change in time. That's our AROC formula that we looked at in maths methods. Okay, so the points in time, where it finds the first 4 seconds, that's the time interval from 0 to 4. So off we go, let's substitute that into our AROC formula. Now, if you think about what we've worked out previously, there we can see from part C, the x at 4 seconds minus x at 0 seconds, that's our displacement from part C. So we get our displacement, we divide by 4. Here it is, and we get an average speed of 8 meters per second. Okay, question 2. The velocity of a body t seconds after it starts 5 meters to the right of the origin, so that's describing the initial position, and the velocity is moving from the origin along a straight line, and it's given by this function. So there's our velocity function. Our job, we have to find the displacement of the body after 6 seconds. Okay, so starting with a velocity function, how do we work out displacement? Okay, well, that's a calculus approach, and we have to think about the direction of we're moving. We're going from velocity to displacement, so that's the antiderivative. Okay, and a displacement, remember, is a change in position. So once we get our position function, we've got to get a change in position to work out what the displacement is. So the position function is the antiderivative of velocity. So let's do that. We've got there's our velocity function. Let's take the antiderivative of each term, and we get this, our negative 2 on 3 times t to the power 3 plus 12t squared plus c. So here's our plus c, and we have to work out what that is. So we're going to draw on our initial condition to get our plus c. And there it is. So we sub in our initial condition. Alright, initially the object was 5 meters to the right of the origin, so in the positive direction. Substitute that in, and we get c is equal to 5. So there it is. There's our full position function. Alright, so now let's get our displacement. That's our change in position, x at 6 minus x at 0. Let's do that substitution. There it is. And simplify, and we get that 288 meters. Okay, so important idea there. Displacement is always a change in position. Final position subtracts some initial position when t is equal to 0. Okay, part B. Find the time when the acceleration is 0. Okay, so now we're after an acceleration of the particle. So if we have a velocity function, what do we do to get an acceleration function? Alright, well, that's another calculus approach, and this time to get the acceleration and work out when acceleration is 0, the acceleration is the derivative, the first derivative of velocity with respect to time. So we differentiate our velocity function, there it is, negative 4t plus 24. And we equate that to 0. There it is, and we solve for t. And we get 6 seconds. Fantastic. Okay, let's have a look at the next question. Part C. Now let's this time find the total distance travelled at the time when the acceleration is 0. So we got the time when the acceleration is 0 from the previous question. That was 6 seconds. So now the total distance worked out, okay, that's going to be a calculus approach again. Now first off, let's look at our velocity function here. Now, when we factorize our velocity function into a 2t times a 12 minus t, then we can see, well, we've got a negative parabola with an intersection at 0 and at 12. So the velocity function looks like that as a graph. Now, the total distance travelled in relation to the graph is in fact the area underneath the curve. And we're interested in what is the area from 0 to the point where the acceleration is 0. Well, that's at the time when t is equal to 6. So we're finding the area under the curve. And how do we do that? Well, the total distance being the area under the curve, that is our definite integral. So there it is. We're going to take the antiderivative of the velocity function. We're going to evaluate our definite integral from 0 to 6. Okay, so the antiderivative of velocity, it gives us our position function. And we're going to evaluate our position function from 0 to 6. And there it is here. And what we notice, we might say, hey, that's like a change in position. And in fact, you'll be correct. This is the same as the displacement that we worked out from part A. So in this problem, for this positive area under the curve, our total distance traveled is the same as the displacement that's occurred. And that's 288 meters. Okay, but you've got to keep in mind this is a positive area because it's an area above the x-axis. And we've got no negative velocity. So that means there's no turning around. That's all the object going backwards. So if the object turned around and came backwards, then you've got a displacement and a total distance traveled that are going to be different. They will not be the same. But in this case, it is equivalent. Okay. Let's look at the next question. Question 3. A car is traveling at 30 meters per second when the brakes are applied. Now it is brought to rest with a uniform deceleration in 8 seconds. How far did it travel after the brakes were applied? Interesting. Okay, so how do we approach this? Well, first off, let's identify some important information. The car is traveling at 30 meters per second, so that's its initial velocity before it starts to decelerate. Okay, so u is going to equal to 30. And then we've got a uniform deceleration, so that means the a number is less than 0, and it's uniform, which means constant. We have a constant deceleration, and that's important because that's our key word there, uniform, which meaning constant. We're going to use our Zuvat formulas. Okay. Now, let's continue with that. So, what we need to work out next is thinking about how far did it travel after the brakes were applied. Okay. Another important thing is that the object was brought to rest. Okay, the car was decelerated by applying the brakes and it was brought to rest. So that word rest there means that the final velocity is going to be 0. Alright, so have a look at our parameters. We've got u, v, and the time taken, 8 seconds. So this becomes the most appropriate formula here. U is equal to half times v plus u multiplied by time t. Substitute in your values and simplify, and we get this 120 meters. So that's the general approach for a question like that. Alright, let's look at the next one. So a body is projected vertically upwards from the top of a cliff 25 meters high with a speed of 15 meters per second with the acceleration due to gravity of 9.8 meters per second downwards. Okay, so again we've got a constant deceleration of 9.8 meters, so we're going to use the same kind of formulation, the Zuvat formulas. Now, in this kind of problem, a vertical motion problem, we got to identify some directions. So let's say going vertically upwards, that's positive direction, and going down, it's going to be negative direction. We've got an initial velocity of 15, so u is equal to 15. And we've got the acceleration due to gravity, 9.8. Well, that's in the direction downwards, always down towards the ground, so it's going to be a negative 9.8. Okay, so the job here, what is the time taken for the stone to reach its maximum height? So let's have a look at the little diagram I just drew. The maximum height is at the point way up here before it starts to come down. Okay, so what do we know about objects that reach its maximum height? Well, that's its turning point. So that's when the velocity is equal to 0. That's when it comes to stop before it returns back to the ground. Okay, so let's work out the time when the final velocity is 0. So we've got an A, acceleration, we've got a V equals 0, and we've got U is equal to 15. Okay, we've got to work out time. So what's the best formula that uses those parameters? That's this one, V equals U plus AT. So we substitute our values and we solve for time. There it is, and we get 1.53 seconds. Okay, part B, the maximum height reached with respect to the ground level. The ground level is all the way down here. Now, what's the difference from where it was thrown to ground level? That's this 25 meters high above the ground. So we're going to use that information this time. Now, this here might be the best formula to use, where we're interested in finding the maximum height here. Okay, where now the maximum height is the final velocity is 0. And we're back. So maybe if we weren't able to answer question 1 well and get the time to reach the maximum height, we could in fact use a different formula that doesn't need time in its calculation. And that's where this formula is useful. V squared is equal to U squared plus 2 times A times X. Okay, so our job here is to work out what is the maximum height. Well, that is going to be our displacement quantity x here. Okay, but we have to keep in mind we're finding the maximum height relative to the ground level, so we'll do that bit next. So first off, let's substitute our values that we know into the formula. It's when maximum height is reached when v is equal to 0. We've got our initial velocity of 15 and an acceleration of negative 9.8 meters per second squared. Alright, so let's put that in and let's solve for x. There it is, 11.48 meters. Now that's 11.48 meters from the top of the cliff, but the cliff is 25 meters high. So altogether, from the ground, our height is going to be the addition, so it's 36.48 meters from the ground. Okay. Moving on, let's look at question 5. So now a vehicle accelerates uniformly from rest for 10 seconds to a speed of 16 meters per second. Then it maintains this speed for a further 20 seconds before decelerating uniformly to rest after a further 15 seconds. Okay, so our job here is to draw a velocity versus time graph that represents this motion. Okay, so let's break it down. So the first part, there it is. A velocity accelerates uniformly from rest. So rest meaning velocity is 0 down here. And it's accelerating uniformly, which means it's got this constant increase, constant rate of change. So that's a linear flat line. And it does that for 10 seconds. So you've got a run of 10 seconds along the t-axis, the time axis, and then a rise of 16 up to a velocity of 16 meters per second. There it is. Then it's going to maintain this speed for a further 20 seconds. So maintain the speed means a constant speed of 16. Jump, there it is. So a further 20 seconds on top of 10 seconds brings us to 30 seconds. Now let's decelerate uniformly, which means constant deceleration, linear, straight line. And we're going to go to rest. Now rest means 0 again, velocity is 0 down the bottom. And we're going to do that over a further 15 seconds, say from 30 to 45 seconds. We're going to have a straight line going down. And we end up with a trapezium. Yeehaw! Next part, part B, let's find the displacement of the particle in the first 25 seconds. Alright, so got to think about displacement being a change in position, okay, and it's also similar to the area underneath the graph. So the area underneath our graph, there's our little graph thingy again. Our graph is a trapezium shape, so the area underneath the graph is finding what is the area of our trapezium from 0 up to half there, our 25. Alright, so some things we need to know about the trapezium. We need to know the height of the trapezium, which is 16. We need to know the top length, okay, which we work out to be 15, and the bottom length 25. So area under the graph is our displacement, and we're working at the area of the trapezium. Half times the A length plus the B length multiplied by the height. There it is. So let's substitute our values in, and we get 8/40 is 320 meters. Fantastic. How are we doing? Well, we're doing well. We're up to question 7. Let's keep going. We're almost there. Now, a weight is suspended from stationary cables, as illustrated below. Oh, look at that. It's like hanging someone's lunch above a pit of crocodiles. Why not? So, it's 20 kilograms, and we've got this cable, X to Y, at 45-degree angle, and we've got this cable, X to maybe some other point, let's call it Z, why not, at 60 degrees. Now, our job is to calculate that tension in the cable. So that's the force of tension that's in this cable. T to X, so it's this one. Okay. So always when we're looking at forces, we use Newton's second law. The sum of all the forces, our net force, is equivalent to the mass times the acceleration. Okay. Now, what do we know about the situation? Well, first off, it is suspended from stationary cables, so it's not moving. So what can we conclude? Well, if it's not moving and it's stationary, we can say something about its acceleration. Its acceleration will be 0. Thank you. Okay, so first off, a force that's acting on the mass is the weight force. And the weight force, there it is 20 G's vertically downwards in newtons. And we've got another force, which is this cable. It's going vertically upwards. Let's call that T, tension force in this cable. So the sum of those forces on this mass, well, they're going to be related to the tensions in these two cables. Alright. Whereas the tensions in these two tables are on angles. So let's break them down into their components. They've got a vertical component and they've got a horizontal component. And that forms right angle triangles. And we're going to draw on trigonometry to work out the sizes of those components of forces. Okay, so let's get our directions organized. Well, let's say vertically upwards is our J direction, horizontally parallel that way is our I direction. So we can break down our forces into their directions and their components. Alright, so let's look at the sum of all our forces. First off, the J direction. What are the forces acting on the mass, our 20 kilograms, in the J direction? Okay, we've got a positive tension force, and subtract a 20 G's of weight force equals mass times acceleration. Okay, the acceleration is 0 because it's stationary. So that means the sum of forces is 0 and we get tension is equal to 20 G's in newtons. Now, this tension force here, that's going to be the same as the vertical components as these tension forces here. Okay, that T will be equivalent to the vertical components of the two tension forces. Okay, so we can conclude that tension T, well, that's going to be the same as one vertical component of this tension force is the sine of 45 degrees, okay, being the opposite side of the right angle triangle, sine 45 degrees of the hypotenuse, T, x to y, there it is, plus, and the other vertical component of the second cable, this one, so it's sine of 60 times T, x to z, there it is. So this sum, the addition of those two vertical components has to be the same as the tension in this little cable there. Alright, and what do we know about T? Well, T is the same as 20G, is what we worked out previously. So it gives us this equation, and we've got two unknowns in this equation. We've got our two tensions in our two different cables. So there's equation number one. Just by multiplying both sides by 2, we've come up with that simple equation. Now we can't solve that yet because we've got one equation but two unknowns in it. So to solve this we need a second equation with those same two unknowns in it so we can solve them simultaneously. So how do we do that? Well, we have to consider the horizontal components of the tension forces in the cable. So that's the adjacent side of the right angle triangles. Alright, so the cos of the angles, now they're going to sum up. We've got positive going this way, and we've got negative going this direction, and that gives us this, and that is equal to 0 because the cables are stationary. So the sum of forces is equal to mass times acceleration, and if acceleration is 0, that means the sum of forces has to equal to 0. Okay, and it presents us with this equation here. Very good. Now we solve our two equations simultaneously, and we get this as our result, and there it is, there's our answer given as an exact value. And that's the requirements of the question, and that is in newtons. Fantastic. So how'd you go for that one? So the important idea is to think about breaking down forces into two directions, a vertical direction and a horizontal direction. Okay. So next question is going to look at now our inclined plane, and we have a truck that's on an inclined plane. Stationary truck of mass 1,500 kilograms accelerates up a rough inclined plane with a kinetic friction coefficient of 0.4. Okay, now as you notice, I've changed the values a little bit. So for this question to work properly, let's consider the little edits that I've made. So the coefficient of friction needs to be 0.4. The angle here should have read 30 degrees, and the truck engine applies a driving force, and our driving force is going to be given like this, and that will allow the problem to work out for us better. Okay, so let's consider this one. Now the truck engine applies the driving force up the inclined road. However, what happens is that the truck begins to roll backwards down the slope. Okay, so let's calculate the time it's taken when the truck comes to a stop after it's rolling backwards. So it's going to roll down and then go forward. So what's the time it takes for it to come to a stop? Okay, so let's look at all the forces on the truck. There's the normal reaction force. There's the driving force going up the plane. We've got a weight force vertically downwards. Okay, and the weight force is its mass times gravity, so it's 1,500 Gs vertically downwards. And this is on an angle relative to the plane. So we're going to break that down into its directions. J direction is coming out this way, perpendicular to the plane, and the I direction is parallel to the plane. And that gives us the opposite and adjacent sides of our little right angle triangle here. Okay, now if the truck begins to roll backwards down the slope, it's moving down this way. Okay, so that means here the friction force is opposing its motion. So if it's moving this way, the friction force is going in the opposite direction, up the plane. So that's the direction of friction when the truck is rolling backwards. And that's what we're after. Okay, so now we've got all the forces in the right directions. Let's use Newton's second law. The sum of all the forces equals mass times acceleration. So let's look at the I component. Okay, the horizontal component to the plane, there it is. We've got the driving force going up, so positive driving force. Okay, plus the friction force, 0.4 times the normal reaction force. And then subtract. Now we're going to subtract the force component, horizontal component, due to the weight force, due to gravity, coming down this way. That's this one. This is the opposite side of the right angle triangle, so it's the sine of the angle component. So 1,500 Gs times sine of 30 degrees equals to its mass times acceleration. Okay, at the same time, let's look at the vertical component in the J direction. So you've got your normal reaction force going up, minus, coming down this way, is your adjacent side, so it's the cos component of the weight force. 1,500 Gs times cos of 30. Now that has to equal to 0 because the truck is not moving. There's no acceleration in the J direction, in the vertical direction. It only moves in the I direction. So that gives you an expression for the normal reaction force N. There it is. Now let's take that value for our normal reaction force N and substitute it back into equation number 1. Okay. And we get this expression, put all our values and simplify it down, we get this expression for acceleration of the truck. Make sure you divide by 1,500 and we get this. Okay, so from this equation for acceleration of the truck, we need to work out some other properties like its velocity and the time it taken for the velocity to go to 0. That's when the truck stops. So truck coming to the stop, that's when velocity is equal to 0. So what do we know about velocity? Velocity is in fact, there it is, it's the antiderivative of acceleration. So we've got to work out this antiderivative by integrating the expression. Okay, so you've got here, there's all the constant part of the equation, of the function. So all that in brackets is just lumped together in brackets, and you just got to treat that as a constant. And when we take the antiderivative of a constant, we get the constant times t, 1t. Okay? Now the antiderivative of 4t goes to a 2t squared. And don't forget that plus c, very important. Okay, now what have I done here? All I've done is taken out a common factor of a negative g. Okay, that comes out and it gives us this nice little surd. Okay, as our coefficient. And you just treat it as a number, just a constant number, put in brackets and treat it as is, as the coefficient of t. Alright, so there's our velocity function. Now, let's work out what the plus c needs to be. This is where we're going to draw on our initial condition. So what do we know about the truck? initially before it starts to move. Come back to the start of the question. The information tells us a stationary truck of mass 1,500 kilograms accelerates. So if it's stationary at the beginning, that means its initial velocity is 0. So let's use that information. Let's sub when time is equal to 0, the velocity is equal to 0, and let's solve for the parameter c, and we get c is equal to 0. How easy. Okay, so there's our simple equation for velocity. Once you've got that equation for velocity in full, now we're going to look at when the velocity is equal to 0, and we're going to solve for time. So let's solve the equation when it is equal to 0 for t. Okay, and you do that on your CAS calculator. You set up that quadratic equation and you solve for t. Boom, there it is. T is equal to 0.8 seconds. Aha. So the truck only rolls back for a very short amount of time. 0.8 seconds worth. Okay, very good. So there's a bit of a complicated question. So there's a number of important parts there. Identifying all the forces involved in the problem. Forming the equations of motion using Newton's second law. You got to work out the equation of motion in the I direction, and then in the J direction. Then you solve them simultaneously through substitution, and you solve for A, acceleration. Once you get acceleration, you have to find the antiderivative of acceleration to get the velocity function. Once you get your velocity function with your plus c integration constant, you come back, you read the information to find your initial condition. You substitute your parameters for your initial condition to work out what c needs to be. In this case, c is 0. Then that gives you your full function for velocity. Then the question asks when the truck comes to a stop. That's when velocity is equal to 0. So you make that substitution, v is equal to 0 into the equation, and you solve for time, solve for t, to get your answer. Okay, part B says, now let's calculate the displacement the truck experiences after rolling backwards and coming to a stop. So we worked out about when it comes to a stop. It takes 0.8 seconds to come to a stop. So we have to get the displacement. Now the displacement comes from the position function. Now the position function, again, position function is the antiderivative of the velocity function. Very nice. So let's take the antiderivative of velocity. So there's our velocity function from the previous question. Okay, now take the antiderivative, and our antiderivative t goes to half t squared. Now the half is coming down to multiply the 10, so that's why we've got a denominator of 20. And then the antiderivative of a 2t squared becomes a t to the power of 3 divided by 3. There it is, plus c. Okay, now how do we work out the plus c? We've got to use our initial condition. Alright, that's when t is equal to 0, we have an initial position of 0, so that's the starting line. We work out the c is equal to 0. So there's our position function. Okay, once you get your position function, let's work out the displacement. So displacement is when we got this time. Now approximately it was 0.8, that's what the answer we wrote down. But when you're going to use the answer from a previous question, 0.8, in calculations, don't just use 0.8 because that's only accurate to one decimal place. You need to use the value in a more precise way, either as an exact value or with more decimal places. In this case, 4 decimal places. So I'm using 0.7526 as the number in my calculation. Okay, so not just 0.8 because that's not accurate enough. That's just, a neat way to represent the number. But when you're going to calculate with that number, we're going to use a more accurate version of the value. That's this one. There it is. So my displacement is given by this, the change in position, and I can evaluate that on the CAS calculator, and I get the 0.142 meters, which is about 14 centimeters. It's just a little smidgen rolling backwards. That's okay. Alright, now the last part, part C here, it says find the displacement of the truck after 15 seconds. So how do you think you might do that? Well, we've got our position function. So is it as easy as doing a little substitution as substitute x15 into our position function? Well, unfortunately it's not that easy. Now, the reason why is because there's two parts to motion. The truck rolls backwards, then it goes forwards and accelerates forwards. So there's two things that are happening in that process. We've got the friction force changes direction, and the acceleration changes direction as well. So it creates different equations of motion, and that complicates the situation. So when it's going forward, and the driving force is driving the truck up the hill, up the plane, the friction force is coming backwards, down this way, down the plane. Okay? Now that's a different equation of motion than what we calculated and worked out previously. And that's where this equation came from. So what's going to happen is that the sign here, which is a negative 2 root 3, that will perhaps change and become a positive, and we might get another negative somewhere as well. So it's a little tricky, and we're just going to leave that one for now. We can explore that another time. Okay, here we go. Very last question. Question 9. Now, Mark kicks a ball off the top of a 40-meter building. Why would a person do that? So here's this little Mark character here. He's got his little bandana on. Looks like a little ninja guy. So, Mark's kicking a ball off a building. Now, it has an initial velocity of 15 meters per second, and he kicks it at 45 degrees from the horizontal, as shown in the diagram below. Whereas Carl at the bottom, he's getting ready. He's going to try to catch the ball. Alright, so how far, x meters along the ground, does Carl have to be from the base of the building in order to catch the ball? Right. So, how are we going to work that out? Well, there's two things going on. We've got the ball is going to move horizontally, and at the same time the ball is going to move vertically. It's going to go up and then it's going to come down. So you've got two versions of the motion. You've got a vertical motion and you've got a horizontal motion. So because we've got two directions, we're going to look at this problem using vectors. Okay, so let's identify our directions. Here's your I direction, there's your I vector, and there's your J vector. Now, let's say the starting position here, that's our position 0. Okay, so if we think about our displacement going below 0, we're going to have a displacement of a negative 40 meters. So if the ball goes up and then comes down, it's done an overall displacement of negative 40 meters. Alright. Now, other things we can identify is its initial velocity of 15 meters per second. So, coming out on this angle, 45 degrees, it's kicked at 15 meters per second. So, what is that in the I direction and the J direction? So we break down our vector, our velocity vector of 15, into a horizontal component, that's 15 times cos 45, and a vertical component, 15 times sine 45. So let's write the initial velocity in vector form. There it is. So
velocity is a vector, so there's u in initial velocity, 15 cos 45 in the I direction, plus 15 sine 45 in the j direction. And when we evaluate, we get that 15 times root 2 on 2. Now, our job in this problem is to figure out how far x from the base of the building does Carl need to be to catch the ball. Well, if you look at x, that is a x meters, that's a position from the base in the I direction, horizontal position. Okay? Now, at any point in time, here's the ball at some point in time, there's only one force acting on the ball. Let's ignore air resistance for now. So there's only one force acting on the ball, and that is the force due to gravity vertically downwards towards the ground. Now, that being the only force, okay, it's the ball's acceleration that it's going to experience is this in vector form. 0 in the I direction, because there's no I direction forces on the ball, minus g in the j direction. So it's going down, so it's a negative g. So there's your acceleration. Now, from the acceleration vector, okay, we can get the velocity vector. So the velocity vector is given by this. This is your Zuvat formula, v equals u plus at. Now in vector form, v is a vector, u is a vector, and a is a vector. U is given by this. There is our u vector. The a vector is given by this. So if you add them together, and then times by scalar t, we'll get this as our velocity vector. Okay. So having our velocity vector as such, you've got this nice little formula in the j direction. This is our u minus at, okay, in the vertical. Now, some things we know about the velocity of our ball. Well, the velocity of the ball changes as time changes, and we can see as it being here a function of time. Okay? But at the top of its motion, way up here, that's its maximum height. And the velocity is 0 at its maximum height. So that's an important little property to keep in mind. But for this problem, that's not important. We're not after the maximum height, but we're after more particularly a kind of maximum displacement in the x. It's called the range. So we need to work out what is the position or displacement function of the ball. So from velocity function, what do? Okay, well, we can take the antiderivative again or relate it to this. This is our x equals ut plus half at squared. There it is. Now, in vector form, x is a vector, u is a vector, a is a vector. Let's substitute our vectors we have into here and add them up, and we're going to get this rule. There it is, ut, that's this part, ut in the I direction, plus, and we have our ut minus half at squared in the j direction. Okay, so what we're going to focus on now is the importance of the second part, the j direction formula here for the displacement. So this gives us an important thing to think about. Is the ball reaches its maximum length over here, its range, when it vertically it covers a displacement of negative 40. So as the ball goes up and then comes down, as it comes up and comes down to about here, back at the point at the same level as x equals 0 level, this point over here, then it's done a displacement of 0. So coming up and coming down to there, displacement of 0. But we want a displacement of negative 40. So from here, the ball continues to come down and is displaced by negative 40. So when the vertical displacement given by this formula here is negative 40, then we've got the time taken for the ball to hit the ground. Okay, so let's solve. There it is, the vertical displacement when is equal to negative 40 for t. And we get t is equal to 4.1 approximately seconds. Okay, we're going to use that number in a calculation, so let's use the whole lot. Alright, fantastic. Now, the next part is, we know the time it taken for it to hit the ground, but we don't want time, we want position. We want the x direction. Now, this x position is the x in the I direction. So that's this part of the formula here. This formula, this vector, part of the vector is going to give you our result for x meters from the base of the building going horizontally. So let's take that. We're going to substitute our t number, our t variable value into the parameter t here and multiply by 15 root 212. Now what you can do to get on your CAS calculator is from solving this equation you're going to get some big complex surd. You can use that exact value surd that's on your CAS calculator and just multiply that by your 15 root 212. So you have a surd times a surd and you'll get a more simple result of about 43.9 meters. Okay, approximately 44 meters away. And there we have it. Alright. Now, part B, calculate the final velocity of the ball as Carl catches it. Now, once you get the final velocity, we got to state your answer as a magnitude and a unit vector. Okay, so we got to think about what that is. So the magnitude of a vector is the modulus of v, vector v, where the unit vector is this one, v hat. Okay, so you got to remember, think back to term 1 when we started vectors. How do we work out v hat, the unit vector, and how do we work out the modulus of a vector? Alright, so let's grab our velocity vector from the previous question. There it is. That's what we worked out. That's from part A, our velocity vector. So we have to work out the modulus of v. But we first need to know at the point, the final velocity, when Carl catches it. Okay, now Carl catches the ball at this time from the previous question. There it is. Okay, so we're going to substitute that t value into our velocity vector to get the final velocity of the ball when Carl catches it. Okay, we substitute it in and we do a little calculation. That bit that can be done on a calculator and you might get something like that. Boom. Okay, that's the exact surd, exact value surd. Okay, so the modulus, there's our velocity final velocity vector. This is the v at the very bottom. That makes sense because look at the direction. The ball goes up, comes down. The velocity vector is pointing downwards on this angle here. So it's got this downwards, it's got this negative j value. That's why we've got a negative j here. Okay? Alright, so let's take the modulus. That's it. It's the square root of the I component squared plus the j component squared. We don't need to put the I and the j inside the formula. It's just the number in front of the I and the j. And when we evaluate that, we get this value here as an exact value, exact surd, square root of 1009, which is approximately 31.8 meters per second. That's more than 100 kilometers per hour. So if Carl wants to catch a ball traveling at more than 100 kilometers per hour, he can be my guest. Now let's work out the unit vector. Okay, so the unit vector is vector divide the modulus of the vector. There it is. And there's our vector v, and we divide by the modulus, that number there, we can divide by that third, and we get this as an exact unit vector. Okay, that can be just produced, done on your CAS calculator, and you just record or state your answer. Alright, fantastic, we did it. Alright, well done everyone. Please review and practice and ask questions if you're unsure about something, and thank you for watching.